So now we're going to delve deeper into integrals by substitution. This will help us refresh some of the topics you might have seen last semester in differential calculus, and it will help us advance into integral calculus. So substitution is quite important because it reminds us how to find derivatives, and it will be very important when you get to integration by parts and differential equations. So we have this very simple exercise of a real life application that we're going to solve by substitution. So imagine that you work on a construction project and you're calculating the time it will take to fill a water tank with a pipe that has constant rate of water flow. The flow rate, f of t, is a function of time, t in minutes, and can be modeled by the equation f of t equals 2t. And you must find the amount of water that has entered the tank in 5 minutes. So the first thing we must do is try to understand what they're asking us, right? So they're asking us to integrate the function f of t, which would give us this dt, and they're asking us to find the amount of water in the first 5 minutes, which would make it a definite integral from 0 to 5. We must look at what can be substituted. So we want to substitute 2t with u, and we want to substitute dt, right? But we still don't know what it can be substituted with. So how do we find that? Well, we have to find the derivative of both sides of the function of the equation, which would give us the derivative 2t is 2 dt, and the derivative of u is du, right? So now, to leave the dt alone, we should divide by 2, which would also divide by 2 on the other side. So now we know that dt is equal to du over 2. And now we can plug in those values into the equation, which would give us the integral of u du over 2. And now, we would like to have some limits, right? But they cannot be the same ones as the past equation because the limits have changed, right? Because we have changed the variables. So what we can do is that we can take the definite integral from u of 0 to u of 5, right? And well, since du is accompanied by a constant, what we can do is take that constant out. That's something that you can do in integrals. You can take it out. So this would equal 1/2 of u0, u of 5, of u du. And now we can solve this integral with what we know from antiderivatives. So we know that the integral or the antiderivative of u is going to be u to the n plus 1 over n plus 1. So we can rewrite that as 1/2 times u squared over 2, right? And this is going to be from u0 to u5, right? And now we have to solve this, right? But it's kind of ugly, right? So we should replace the variable back to t so that we can have the same limits as we had before. So let me erase all of this so we can have more space. Okay, so now we have that if we replace it back, it would be 2t to the square over 2 solved from 0 to 5. Now we have to solve this equation, right? So we know that this would be 2 of 5 squared over 2 um, minus 2 times 0 squared over 2. And what can we do here? Well, we know that the 2's cancel out. They always do. The 2 cancel out. And well, anything multiplied by 0 is 0, even 0. So this whole thing would just be 0, and we would be left with 5 squared. And the answer to this integral, so the integral from 0 to 5 of 2t dt would be equal to 25. Okay, so we solved it mathematically, but I would like you to have a graphical reference for that. So it's going to be easier to learn. And well, in the internet, you can find PhET, which has a lot of simulations, which are amazing. This one is about calculus. You can find chemistry. There's almost simulations about anything. Okay, so we had the integral of 2t, right? So if we do this, we make it a bit slanted like that. And we can now clearly visualize that the integral of 2t is going to be t squared, right? We can see right here. Looks very nice. It's a parabola. It makes sense with what we calculated. And well, now I want to show you another cool app from the internet that helps us with visualizing it, and it's Desmos. So if we enter y equals 2x, which is the equation we had, we're going to get this. And the integral is going to be the area under the curve, which would be y smaller than 2x. And we get this beautiful line, and we can get any value. We see that it goes infinitely on. So this is practically the integral we had. We just did it from 0 to 5, which would be this small area here. From 0 to 5 would give us 25. And yes, another way to do these visual calculations, and that is very good, is Wolfram alpha. Right here we can come and integrate 2t with respect to t, and it will also give us the parabola that we saw in PhET. Very nice. And we can also do a definite integral from 0 to 5 to t. Okay. And that's going to give us this, the shaded area from 0 to 5 that we got in Desmos. It's the same thing. Looks very cool. So now you have three different ways of visualizing it, of helping yourself when you're solving these kinds of problems. Sometimes they're going to be harder than the ones I showed you. So these tools can be quite helpful, actually.